did in class. So I'll let you have fun with that one. It's pretty simple. While playing a thrilling game of Mario Kart, you notice an oil slick on the ground. Unfortunately for you, your next-gen system that you paid 8,000 schmeckles for will not process the thin film interference. Your immersion has been ruined. And that's the worst, right? When your immersion gets ruined, it's just... So to remedy this, you set out to modify the codebase, assuming that the daylight in the game has a peak at 550 nanometers and is monochromatic. We know it's not, but let's just assume for a second that it is. And that the oil has an index of refraction of 1.54. What would the depth of the oil be to see this constructive interference, or the light at a maximum? Okay, so if we're looking at this, this is the intergalactic problem number 12 of chapter 24, wave optics. Okay, so if we're looking at thin films, what we need to do is we need to set up our actual interference. What the heck is that? So remember, what's going on with thin films is that the light is reflecting off of the different boundary layers, either with a hard or a soft reflection, and some of the light is passing through the thin film itself, adding a distance of the thickness, or twice that, to the light's pathway. Now remember, this light is actually always traveling perfectly up and down, but that makes it really hard to look at. So we're going to draw it at a slight angle. So what happens here is we have some light come in, and it reflects off this boundary layer. So there's a reflection right here. And then the light continues to move and reflect again. There's a reflection at this boundary layer, and the light has traveled through a thickness of T. It has traveled through that thickness down and up. So what we're going to do to set this up is, if we'd like to find a bright fringe, and if we think about wave interference, normally if our change in length, our change in path length of the light, delta L, is equivalent to an integer of that light's wavelength, that means the light is going to go back into coherence. It's going to go back in phase with itself. We're going to have a bright point. This was true for the double slit when we looked at it. The single slit, this actually gives us a dark here, given the way that the single slit works out. It's a little different. But in general, a change of path length equal to a wavelength will give us a bright point, okay? For M as minimum as you can get it. So if we look at this here, we're going to have two change in path lengths that we need to set up. Up here for this first, this is delta A. It is just a reflection. And down here, we're going to have delta B. It is a reflection plus a path length difference. So for delta A, let's find that. In order to do it, we need to know the index of refraction of our various layers. This up here, N1 is an air, so it's just a value of 1. We know N2 is the oil, 1.54, and N3 is the back edge of the oil, or like the hard ground. And this index of refraction here, we could call it like infinite. We're not going to get any light propagation through that. We're just going to get a hard bounce off. Okay. Maybe it's better if I actually just tell you what that value would be, but let's just call it infinite for now. Let's force the hard reflection. It doesn't matter what it is. We just need to know if it's larger or smaller than the 1.54. So the delta A up here, when we look at it, we see we're going from an index of refraction of 1 to 1.54. So that's a hard reflection. So we're going to get a wavelength shift of lambda over 2 out of it. For the N2 to N3 for delta B, we're always going to get 2t because we've got 2 times the thickness we're going through. And then we have to ask ourselves, is this a hard or soft reflection? Well, we're going from 1.54 to infinite, so that is a hard reflection. We have to add a half wavelength shift here as well. Okay. Delta L is always delta B minus delta A. So when we do this, we're going to get 2t plus lambda over 2 minus lambda over 2. That makes this easy. So we're going to get 2t equals m lambda for a bright point. Okay. We knew in this problem, I just gave it to us, that the lambda, or the peak of our monochromatic daylight, is 550 nanometers. That corresponds to a green, and that is kind of the peak of our sun. So it's not too crazy. But if we're looking for a bright peak here in this minimum thickness, then what we can just say here is we can just say if m equals 1, and it has to be 1 here, because if we set m equal to 0, you'd have 0 times lambda equals 0 thickness. So that doesn't really like further the problem. So m equals 1 here. So what we're going to have is simply that the thickness is equal to lambda over 2. We need to be careful here because this is actually the lambda in the medium, which means if we think back to what we did when we were talking about Snell's law a while back, we know that the wavelength in the medium is equal to the proper vacuum wavelength divided by the index of refraction. So what we're actually going to have here is this is equal to lambda proper divided by 2n of the medium we're in, the oil. If we churn all these numbers together, we get 550 divided by 2 divided by the index of refraction of the oil, 1.54. We see that our thickness here, since this was in nanometers, the wavelength, and the index of refraction is unitless, our thickness here is 178 nanometers. That's what we get here. Okay. Every time we do one of these problems, it's best to set up this scenario. Remember, hard reflections, we get a wavelength shift of lambda over 2. Soft reflections, whenever our initial index of refraction is higher than the one we're going into, we get nada, nothing happens. We just move on with our lives. If we set that up each time, we find delta L, which is delta B minus delta A, and set that equal to m lambda for brights, or if you are doing darks, m plus 1/2 lambda. That's for a minimum point where it would appear black or dark. You just run through the same thing each time, work out the math, solve what you're looking for. Make sure when you get to the end here that you think about the proper wavelength that you're given, and how that wavelength changes as you go into your thin film itself. And if you do that, you should be pretty much set for a problem with the thin films.